Okay, so let's have an example for a cyclic cyclo for a cyclic compound, no? Where we do dehydrohalogenation. Okay, so you have your substrate, you have your leaving group, and you have your alkyl substituents, and our base is sodium ethoxide in our solvent methanol. So what will be our major product here? When you have this one, it's best if you can show in the let's say, chair confirmation. No, so let's say chair, showing the chair confirmation this. Okay, so you draw two lines. Let's see, you can draw two lines. Yeah, it's not perfect. So you have that. And you have your CH3. Let's say this is our Cl. So you have your up, say up, down, up, down, up, down. Of course, you have your Cl. Kung nag-equatorial daan si Cl, no? Para klaro siya. And then you have your, say this is our carbon 1, carbon 2, you have your C6H5 here. And, sorry, they are in the same position behind. They are in the same position, so it should be in equatorial, C6. So up should be in the same position, so it should be in C6H5. And then you have your CH3, which should be in the opposite as your Cl. Okay, so if it's up, then it should be down. So two down away, two carbons away, CH3. Okay, so Cl and C6H5, they are on the same position, same side, so up, and CH3 should be on the opposite side of the plane. So we have up and there should be down here. So the rests are made up of hydrogen. So di na natin naibutang, i-reason na lang natin ng uban. Okay, so now let's look at for a hydrogen that is the have your adjacent. Ay, sorry. Shouldn't be here. Okay, so the Cl is a carbon die next to your chlorine. Okay, so it should be on, if this is down, okay, the other is up. And they're on the same side, chlorine and C6H5 are on the same side. So you have C6H5 and you have here your hydrogen, okay? And you also have your hydrogen here, tama? Down, and you have a hydrogen up, which is in the equatorial position. Okay, so there are two kinds of proton. That what is our base here? It's ethoxide. Ethoxide, so ethoxide is simply, you can write CH3, CH2, hindi na masulat. AO minus, so there's that, that are 6, of course, electrons or unshared electrons. So we'll abstract now. We'll use this to abstract. So there are 2 anticoplanar protons, right? This is up, this is down. I already write na lang para dili ta mag-flip-flip, no, dali lang. Of course, let's see. They're already in equatorial position, so they are stable already. So we can abstract this proton. Okay, when we abstract this proton here, the bond between carbon and hydrogen will go here. Okay, and once the bond is formed, then the leaving group will leave, taking with it the electron pair. Okay, so you notice when you do the elimination reaction, or even in any reaction, no, like substitution or elimination, we always find where our electrons are, and that's where we start with our arrow, whether we abstract or we attack. So here we abstract the proton, so our arrow should be directed to hydrogen. Okay, and here the arrow starts from the covalent bond paingon sa kani in between this bond, because this is where the double bond occurs, and you have this one here. Okay, so you have, of course, para di mo maglibog also, you can count, no, earlier. So you have to this didn't count. So this is our carbon 1, this is our carbon 2, carbon 3, 4, 5, and carbon 6 here. Okay, we have carbon 1, carbon 2, carbon 3, and carbon 4, 5, you have 6. Okay, so up, down, you can check up, up, or same side, and we have down. So you can do the reaction. You get your product. Para mas dali, no? That's wrong. Okay, so you have your, let's say, carbon 1. It's carbon 1. You form a double bond, and you have your C6 H5. Okay, and you have 1, 2, carbon 3. You have your 1, 2, 3. You have your CH3. And the other one, if this atom attacks, I will use an orange. If this oxygen attacks this proton, which is also anticoplanar, okay, what happens is the bond here will go there between carbon 1 and carbon 2. Okay, you have an arrow. And of course, the bond between, once the double bond is formed, the chlorine will get the double bond, the pair of electrons, now when it leaves. Of course, you have the side product here. Chlorine is your side product. Cl minus. Cl minus na siya. Of course, na siya 6 electrons, right? And then, of course, you have your CH3, is your other product, side product, CH3, or ethanol na lang. Your other side product, which is CH3, CH2, OH, no, forms a bond. And then if this one is the product, if this base attacks this proton here, you will get you will have this. This is carbon 1. You will have, say this is carbon 1, carbon 2, and 1. You have a double bond, okay? And on carbon 1, 2, 3, you have your CH3. And then 4, 5, and in carbon 6, you have your C6H5. Okay, so you will ask which one would be the more stable one, or not stable, the major product rather. Of course, you have your side product. This other two here will also be your side product for this, but this is a one-step reaction. So you will have to determine which one is your major product. And of course, it follows the Zaitsev rule. Since it follows the Zaitsev rule, this one is our major product. So this is our major product. Major. Let's see if sakto ba itong answer. Okay, so your major product is the one where it has the C6H5, okay, carbon 1, 2, 3, you have here. And we're showing the eye here, they are showing whether it's the same side or opposite side. You can follow on what's the original, this one. So you have your CH3, CH3 should be right up. And the other one is also up here, same side. And this one is ganito. Broken. Okay, so this one should be broken. And also this. Okay. It's so nice to write on paper. Okay, hope that is clear. So elimination reaction actually is very simple to follow. You just have to know what is your base to be, what is your proton to be abstracted, and you always go with your arrow and dali rin mo siya mabalaan where will it be, where the double bond will be. So practice 7.10. Ika mo na lang ani. When cis-1 bromo 4-terbital cycles is treated with sodium oxide, it reacts rapidly. So this is again a cyclic compound. The product is 4-terbutyl cyclohexene. Write the conformational structure and explain the difference in reactivity of the cis. Okay, dali na siya in 7.11. Okay, so I have already discussed, I think, the E1 reaction last time, no? In the E1 reaction, so there are two kinds of mechanism. This is already a review and redundant to what we have discussed in chapter 16. But since in the 12th edition of the Solomon's textbook, no, this one is discussed in chapter 7. So I just have included here Okay, but do not forget on the mechanism of the reaction. It always starts, the first step in the dehydrohalogenation is always the formation of the carbocation before the base obstructs the proton and you get your double bond. Okay, so you get a two. The one that I've shown earlier in the previous slide, no, sa yung kang 11th edition nila, they actually shown the curves here in the reaction, free energy reaction coordinate diagram. They've shown three curves. No? Since here we only get two steps, you get only two curves because you only get two transition states. Okay? So just have to correct on that. So chapter 6 no slides because that's what the 11th edition of the Solomon's textbook have shown. But in reality, since we only get to two steps, there's only two curves that we see since we only have two steps. So this is your initial reactant, transition state product. So product of the first step becomes the reactant of the second step and transition state and the final product here. Okay. Also in chapter 6, we've learned how to favor an E2 mechanism. So you're given that. We use secondary or tertiary alkyl halide to favor E2. When we use primary alkyl halide as a starting material, as our substrate, then we use a bulky base so that it favors elimination reaction. We also use a strong, highly concentrated nucleophile and non-polarizable. Why? Because a weak and polarizable base would not drive the reaction towards bimolecular reaction, thereby allowing a unimolecular process. Sodium ethoxide, we also use sodium ethoxide and tert butoxide. These are the usual bases that mostly we encounter now when we do the E2 mechanisms. They are, why do we use this one? If you notice in our example, no, we use a tert butoxide, we use the ethoxide, no? The reason why we use this one is because they follows the 1, 2, 3 criteria to favor the E2 mechanism. And then of course, at an elevated temperature, we also favors the elimination reaction. So I'd like you to review on chapter 6 on what are the criteria that would favor SN1, SN2, E1, or E2. Now, before you proceed on solve problem 7.6 here. I think we already have also an example of this in chapter 6, no, the last part of chapter 6. So give the product of the reactions. Of course, always remember there are competing reactions. And we see here, this is kind of elevated temperatures. Expect this one to be an elimination reaction. This one. See, the temperature is kind of elevated. So if you have a competing product to do the substitution, the majority of the product will always favor the elimination, and you get an alkene in the product. Okay, so this one, see the temperature is elevated. This one is at room temperature. And then you look at the substrate, is it primary, secondary, or tertiary? And you look at the base, there are this is the usual reagent for an elimination reaction. Okay. So letter A, of course, it's an elimination reaction, the major product. It's not CH3O, because this is our substrate is primary. Okay, it's a primary one, primary also primary. So because it's a primary, it favors the SN2 reaction. No? Letter B. So we change the base, and since our base is bulky, okay, it favors the elimination reaction. It couldn't follow the substitution reaction. This one is a primary. So in the SN2 reaction, there is a concerted, it couldn't be an SN1. No? This one, there is a concerted reaction that would attack this carbon here to substitute. So your product will be CH3, CH2, CH2, and OCH3. Okay, and for the letter B, of course, we follow the major product, the elimination, as I mentioned, since we are using a very bulky base, so it cannot attack, and it couldn't attack, backside attack to this one because it's bulky, you have here, and so on. Okay, so it follows the elimination, and you get your, if this is our alpha carbon, it eliminates this one, this beta hydrogen here, eliminates the beta hydrogen, so you get your double bond in here. So you have CH2, CH3, your beta carbon, and sorry, your beta carbon, your alpha carbon rather, and this is your beta carbon. So when this base abstract the beta hydrogen here, so the bond between carbon and hydrogen will form between this, and you get a double bond. So CH3, CH, no, makuha yan sa isa ka CH, and we have double bond CH2 here. Okay, CH3, CH, double bond CH2. That will be your major product. So you have a weak polarizable base also here. You have a weak base, of course. When you have a weak base, it follows the doesn't follow the elimination, but the substitution reaction. So it always follow the, you have the SN2 reaction, no? Substitution reaction. You always have to remember when you have a weak polarizable base, okay, polarizable siya kaysa ano nila, no? So it doesn't follow the elimination reaction whenever you have a polarizable base. So this one here, you have CH3OH, no? So this is kind of solvolysis reaction. So it follows the SN1, okay? So you have your solvent to be CH3OH. And this one, you have your hydroxide, can follow the elimination reaction. It's a strong base. But you can also proceed with a substitution reaction here. Okay, letter D. So letter D, the base is a strong base and a strong nucleophile. It's a 3-degree halide, therefore you would not expect an SN2 or is the major product. Yes, so we expect this to deprotonate the hydrogen here, so you get, but they are similar, so you get the same kind of alkene, rather you abstract the proton here and here. So this is an elimination reaction. So since this is a tertiary alkyl halide, no, we didn't do the SN2 reaction. But if there is a substitution for possible substitution reaction, then probably the SN1 reaction. Okay. And since we are dealing with a tertiary alkyl halide, no, so we get an E2 for the elimination reaction. So majority of the product will be an E2 reaction. By the way, mind you that this kind of problem actually will come out always in the board exam, chemistry, organic chemistry. So you always have to familiarize, discern very properly what will be the major product and the minor product. So we always need to practice. Let's see, practice 7.12. We are to choose which reaction would give a bitter yield of styrene. There are two kinds of reactions here. You have an aromatic one, but you have an alkyl halide in this part, side chain, and a BR. Of course, you get your alkene here, and you get here. The question is, which reaction would you choose to obtain a better yield of styrene? Explain why. So the difference is your substrate, right? So here, this is your alpha carbon and this is your beta carbon where you have your hydrogen. And so this one can be abstracted. The proton here can be abstracted by our base to get our double bond. Okay, but if you have your living group, this secondary living group, no, we can abstract this one and still get this. So the question is, which one would give a better yield? Is this one or this one?
Number
Number one or number two? Actually, parehas siya, no? It will still yield the same product. They both have the protons, the beta proton. But which one do you think will be easier to abstract? Would it be this or would it be this one? Remember that when we use our base, okay, when we abstract, no, the proton should be anticoplanar. Okay, so if we do the Newman's projection, no, so one of the protons should be the anticoplanar of this. So which one? It's possible you can have an anticoplanar position here. Also here, you both have, it's easy to rotate. You have your, just have to rotate, you get your anticoplanar proton also here. Tama? But the thing is, which one would be much less steric for your hydroxide to obstruct your proton? No? Because this this styrene here can promote electrostatic repulsion with the approaching base. So, in nga position less repulsion when we abstract. Is it letter number one or number two?
Number one. Number two.
So number one. Remember that so number one, when we abstract the proton, now there is this other one, which is very bulky. Well, this one, when we abstract the proton, okay, there is no bulky group that could hinder us. Sure. Okay, the answer is number
2.
number 2, no? But we have to verify. Let's consult our Solomon's book later. Okay, solutions manual intention. So now we can proceed with another kind of reaction to prepare our alkene. No? So the first one is the dehydrohalogenation, where our living group is an halogens rather. For the second one is our living group is the OH, the alcohol. Okay, so this kind of reaction when the living group is OH to do the elimination reaction, we call this as a dehydration reaction. Of course, we still produce our double bond, and one of the side products, of course, is water. So the base will obstruct the proton, and to get your double bond, and your living group is an OH. So let's see how would the OH leave our substrate for the elimination to proceed. Again, the same way with the dehydrohalogenation, since this is an elimination reaction, there are two kinds of mechanism that is involved in dehydration. Still get an E1 and an E2. But we'll see later that there are additional steps that will follow when we do the dehydrohalogenation. So this kind of reaction, the same with the elimination. Generally, the elimination reaction is always favored at a higher temperature. Okay, similar to the general elimination reaction, just like in dehydrogenation, the dehydration reaction also is favored at a very high temperature. Okay, the most commonly used acids in the laboratory are Bronsted acids. What are Bronsted acids? They are proton donors. Examples, we have your sulfuric acids and phosphoric acids, and we also get our Lewis acids are often used. Lewis acids like your alumina, we can have that used in industrial gas phase dehydrations. But what we commonly use are the Bronsted acids. So usually, we look at here, one of the catalysts in the dehydration, we use an HP or an acid. So when an acid is protonated, of course, there's a proton, you call that one, or an acid that donates a proton in solution in water, you call that one as Bronsted acid. Example, your concentrated, your sulfuric acid or phosphoric acid. So what are the conditions in the dehydration reaction to form our alkene? The first one is that the temperature and concentration of acid required to dehydrate depend on the structure of the alcohol substrate. Okay, so primary alcohols like this one, they are very difficult to dehydrate to form. So in order for us to proceed with the dehydration of a primary alcohol, we have to get it at a high temperature. So we have concentrated, very strong acid usually is concentrated acid, and we have at a higher temperature. Okay, so yes, the primary alcohol can proceed to a dehydration reaction, but it is difficult, at a normal temperature or less concentrated acid. So to proceed with the elimination reaction, the condition should be at a very high temperature and uh, concentrated acids. For secondary alcohols, the dehydration proceeds under milder condition, unlike the primary alcohol. So let's say we do the primary alcohol's dehydration at 180, the secondary can do at a lesser temperature and at a very much diluted concentration. Let's say 85% of phosphoric acid, like this in the example, that we can obtain our product. So again, our living group is OH, and HOH is eliminated, water is eliminated, the proton, the beta proton, and the OH is eliminated, and you get a double bond. Here you get your OH and your beta proton here is eliminated, you get a double bond. Also in this case, and of course the side product is always water. For tertiary alcohol, Okay, so if milder and secondary, the tertiary alcohol is much relatively milder, than the secondary also. So if we use only 85% phosphoric acid in the secondary, in tertiary, we use a milder condition like 20% sulfuric acid. And if we use like around 160 temperature degrees Celsius in the tertiary, we get that we perform that one at a lower temperature, let's say 80 degrees Celsius. But also bear in mind that 80 is so much higher than the room temperature where you can easily obtain your substitution reaction. For elimination reactions, we always do at a higher temperature. So here you get a double bond. So there are two beta protons from your leaving group. You can abstract the proton here and proton here also, but of course, since they are the same, it doesn't matter. You get only one product. So you get two protons supposedly, you have three rather. You have beta proton, beta. But since they are all CH3, so you get just one product, the same alkyl groups, just get the same kinds of proton actually. Just in that case, you get just one kind of alkene in the reaction. So for this case, you get a yield of 84%. So in summary, the relative ease if we proceed the dehydration reaction for alcohol to produce our alkene is that 3 degrees is much easier than 2 degree than 1 degree alcohol. So we'll discuss later on the relative stabilities of the carbocations when it proceeds with the E1 elimination reaction. The E1 dehydration reaction. So second condition for dehydration is that some primary and secondary alcohols also undergo rearrangement of their carbon skeletons during dehydration. So let's see, for example, you have here your alcohol, it's a secondary alcohol here. And so you get like our agent to be milder, like 85% phosphoric acid and 80 Celsius temperature. So you get this one, your alpha carbon, where you contain your leaving group. You have your beta protons here, So you only have one beta proton actually, the CH3. Now, so your main product should have been CH3, CH3, CH3C, CH, double bond CH2. This one, CH3, CH3, CH3. But you don't get this. You don't get the CH3, 3CH3. And then you get your proton here. You abstract your proton with the base and get your double bond. But you see in here, you don't get that product. No, so you don't get your product. Instead, you get only your CH3, CA. You have 1, 2, 3, 4 carbons. Main 1, 2, 3, 4 carbon should be CH3, C. Okay, it should have been CH, and then you have your, should have been your double bond CH2 here. No, this one. But what you get is that CH3 is shifted here instead of here. Dapat si CH3 ni mo na diri. You get. So this, in this case, what happens is there is a rearrangement. The primary and secondary alcohols undergo rearrangement in their carbon skeletons during dehydration. So how do they go? How do they do rearrangement? We will see later when